Well, it seems we've all gone quiet, so maybe I'll just break the silence by standing up. Good morning, everybody. My name's Rex Galbraith. I am in the Department of Statistical Science, so-called retired. That means you still go on working, but you don't get paid for work. You sometimes get breakfast. So today, this title, it's a bit longer than the original title I had, which was looking at data, but Sophie sent round this email with a much longer and more grander title, looking at data. So there it is. But she's asked me to come and say a few words about looking at data, suggestions of certain things to talk about, and so I'll try and do that. I've got some slides here. It's very formal for a breakfast time to have an slide saying introduction, but this is an introduction to me rather than to anything else. And the main thing it sort of says here is that though many statisticians work in fields like medicine, medical sciences, biological sciences, economics, not so many actually work in physical sciences. And I understand that a lot of people here are of physical science background, physics background, and physical science background. And so I have had the pleasure, and sometimes the pain, of working with physicists, in particular in the area called fission track analysis, which is actually a geological method for estimating thermal histories, geology. And more recently in optical dating, optically stimulated luminescence dating, which to me is science fiction. They think they can date things by measuring light that comes out of quartz grains that have been buried. And sometimes it's almost convincing that they measured something which is right, but no one knows why it works. So I have had those, and I'm still working in some of these fields as well. While I'm on the subject, if any of you, I do actually give a course for the graduate school in UCL called Statistics for Researchers as part of their so-called skills development. I think you develop these skills of you go along and learn statistics and then you have this skill. To me, it's not so much a skill as an understanding of what it is you're trying to do. And so I keep trying to tell them that we're trying to get people to understand how to do things, how to look at data and what they mean. So I'll carry on. What's the seminar about, looking at data? Right. What are data? And this is the first thing. It's obvious. You go to course on statistics and you get some data. But it's a bit of waffle here, but we like to have a concept to think what as a form of data, what we call data. And I've broken it down to a thing called data structure and quantity. How much data, how many observations have we got, but the data structure. And we like to think of it sort of sometimes as you might imagine it in a computer file. When you do your analysis or your data collection or your experiment, and then you somehow organize it into a computer file. And we think of it, usually has rows and columns. And the different columns are usually different variables that you've measured. And the rows are usually different individuals or cases that you measure those variables on. And that's a very general type of data structure. So we think of it being observations or measurements on one or more variables on each of a number of individuals. And then the question arises, what is an individual? What regards an individual? Is it a person? Is it a school? Is it a day? Is it a quartz grain? Or whatever it is the individual is. That's one thing. And then are they grouped in ways that should be allowed for? That's part of the data structure. And what variables are measured on each individual. And we have in statistics, we have this concept of we don't necessarily regard all variables as being on equal status. And we think of response variable, that's the thing we're interested in, the response or sometimes the outcome variable in medical trials. And we often call it Y. And we have explanatory variables, which are usually called X, which try to explain how Y varies. And so we have a general question: is how does Y depend on X? That's the sort of concept we try and get. These are very general concepts, but I'm trying to get the sort of context for looking at data. Furthermore, we may have explanatory variables divided into those that we really care about, what we're not interested to study, which we call X, and those that have no special interest that we have to allow for when we're comparing Y. We call them covariates or confounders. Typical type of example, certainly in observational studies in medicine, how does the outcome, how does some outcomes such as death from lung cancer depend on exposure to smoking or passive smoking? So the exposure to smoking might be X, the outcome cancer might be Y, and we have other variables there which are usually age and sex of the individual concerned, which we have to understand because the way Y depends on X, it does depend on Z very often. And that's a general type of question. So data structure and quantity, data quality. Where did the data come from? I'm not going to spend today talking about that sort of thing, but it is very important to understand where they come from and how measured. Different types of studies, design experiments, observational studies, surveys, and many other types of data. Also, what I'd like to call hard and soft data. There's no technical definition of hard data or soft data. Physical sciences has more hard data than say, social sciences in general terms. But you can get soft data in physical sciences. There's things that are transient, but we measure them again the next day, they're different, that sort of thing. They're fairly soft. You can't sort of put the data away in the drawer and come back the next day and measure again and get the same answer sometimes. Happenstance data, you just happen to have some data, someone's left, people, researcher in your office left some data there and you've got that and you then spend your life analysing that. But you have to, this is very important just in terms of interpretation of what you're trying to do. But here are some data. So I've just grabbed a data set from the R datasets package. So I do a lot of my computing using the package R. People use R here? Yeah, good, yeah. So you'll know what I'm talking about. And this is some environmental measurements, ozone concentration, and there's a small print telling you where it comes from, solar radiation, wind speed, temperature in degrees Fahrenheit. This is historic 973 in USA. But there's, and it's measured on each day for a period of about 150, about 5, 6, 7 months, from May the 1st to somewhere, September or something. And so there's some data, and I've given you the first 7 rows and the last 3 rows of the data matrix there. And so there's a structure of data, pretty simple. They're time series data with 4 variables measured once a day. And the first thing you do with data is to plot a graph of them. So I have plotted a graph of these just because I've got it there. I can't show you the data without plotting a graph of it. It's one of my reactions to do that. And there I plotted the 4 time series simultaneously going along, standard time series plot. It's not quite as standard. If I ask the student to give them that data matrix and go away and plot the data, they wouldn't come back with that plot. If I said do a time series plot, what they'd probably do could be 4 separate plots, one on each page. So the first thing is put everything together on one page. Have a look at it if you can. And another trick that people don't really know with time series plots, they're much easier to look at if there's not too much variation in the on the y-axis, in the y direction. So I've got the y scale very short and the x scale very long, and you get a visual perception is much simpler than that. Even so, you can't see all that much. The smoothest of these is temperature. You see it going up. There's a period here with high temperature. Temperature is high for quite a few days in a row. And it goes up smoothly and goes down smoothly, scatters around. So temperature is quite smooth. Ozone comes along quite low, then occasionally it goes up, and so on. Notice there are missing values. I didn't mention that on the previous slide. The missing values, labelled MA, not available. And that. Anyway, there's some data. And at least when you look at that, you try to see how they vary by themselves, each variable, and how they vary together. You can try and guess that. And you get a few clues. There's a sort of high ozone here, and there's a relatively high temperature there, and a high, but it's not. You can't see all that much of that, but you can see generally how the data behave, and there are things there that are not there. That's worth knowing. There are no really extreme values. There are no big outliers anywhere. That's good. Or it's bad if you think they might be thrown away. So the question of, that's one of the reasons for plotting these. So what have I got here? I've got a slide here which is a bit more, tells you about statisticians think of different phases when you're looking at data. What are you trying to do? And a lot of work is to do with preliminary or exploratory data analysis. Just get the data and see what they're telling you. You can go a fair way doing that sort of thing, and that's mostly what I'll be talking about today. Looking to see what they're telling you. But data by themselves don't mean anything by themselves. They have to have a context. Otherwise, they're just numbers, and that could be anything. So whenever you look at data, you're looking at it from a point of view of some context or other. But there's more formal analysis, model fitting, and so on, model checking, and presentation of results. So graphs and tables come into these areas here, but I'm not going to be worrying too much about that today. So one of the things that Sophie asked me to mention was types of data, types of variable, just to put this slide up, and I don't want to talk about it too long, but we think of two broad types of data, qualitative and quantitative. Quantitative actual measurements. Physical sciences deals, I think, mostly with quantitative measurements, and we would break those down into two types, effectively continuous, things that can basically have any value if you measure them accurately enough. Weight, length, time, concentration, measured sufficiently accurately. One of my dictums to students of statistics to tell them all data are discrete. All data are discrete. Remember that. But if they're measured sufficiently accurately, then you can certainly model them with continuous random variables and that sort of thing. So, and discrete, usually integer values, number of failures, size of family, number of events in a fixed time, and so on. Count 0, 1, 2, and these have special properties which you like to preserve when you're A, graphing them, and B, working out models to explain them. The other sort of types of variables, qualitative, ordinal, ordered categories, degree class, first, upper, second, lower, second, third, and so on. They're different categories, but they're ordered. First is higher than upper, second is higher than third, and so on. Severity of disease, mild, moderate, severe, a lot of data of that type, and there are special ways of looking at them and special ways of modelling them. Nominal, in a way, or just unordered categories, blood group, eye colour, I suppose, I don't know. It's really quite hard to think of really nominal, but city, region, schools, when you just have units which are just different categories, and you're looking at variation within the between. And then a very common form of data is binary data. There are only two possible forms, sex, male or female, two types. Disease, present, absent, outcome, live, die, and so on. And one of the points, and there are special ways of modelling or modelling those. You tend just to look at proportions and frequencies when looking at binary variables. The one point about this is you can reduce any variable to a binary variable if you just by categorising the values of the variable. If you can have age, it might be a continuous variable, then you can just have above a certain age or below a certain age, and then that's a binary variable, old or young. So these will sort of come out when we look at data, I suppose. I'm going to be mostly talking about continuous quantitative data today. Now, what are we trying to do when we graph data? I don't know whether you've ever seen the book by Edward Tufte, E.R. Tufte, the Visualization of Quantitative Information. classic book now, 1983, published. Brilliant, brilliant book, and he's written several others as well. And if you don't know it, get a copy. It's a beautiful book. And on page 1 it talks about graphical excellence. And item 1 on page 1, what are you trying to do? Graphic says, show the data. And without distortion. So any book on graphics should tell you to try and show the data. Not as easy as it looks, some of these things. Try and show it in the way that brings out its logical structure. It's a logical structure that should come out in the way you're trying to show the data. Put many numbers into a small space. So high density graphics see much more use, especially for exploratory analysis, than low density graphics. Low density graphics are what you see in corporate reports on financial. A beautiful glossy thing with one huge pie chart in the middle, beautiful colour, telling you about 5 different numbers. That's it. Put many numbers into a small space. Try and get things together. Put things to be compared close together. These are the things we try and do. Make large data sets coherent and reveal data at several levels from a broad overview to fine detail. I won't be doing all that much of this morning because I'm going to talk about sort of 4 basic things, but some of these things are going to be like graphical elements. When I talk about histograms and box plots and things, you can do graphs which each element is itself a box plot or a histogram. And this is the sort of thing that we try to do when we graph data to look at it. So when I went to school, I was taught to plot a graph of x against y against x by the math teacher, Cartesian coordinates. I got this graph paper and they made me rule a line right at the edge of the margin on the left-hand side, another line right at the edge of the margin on the x-axis, and very, very carefully in pencil, not in pen, because you might make a mistake, you can't rub it out. And then there's no room to write the labels on the x-axis, suddenly you realise that. And then suddenly you've got this graph, there's all this empty space in the middle of the page, and there's all the information. A lot of the information in the graph is in the axes themselves, in the axis labels. That's information. So you want to be able to read that as well as the graph. But the way we were taught graphs to write graph at school was completely the opposite of what we really want to do when we look at data. We want to shrink graphs right down small so we can see plenty of them together and look at them nicely. So, okay, let's get on. Plotting one variable, I'm going to show a few different types of, just plotting one quantitative variable, dot plots, box plots, histograms, kernel density estimates, and what you do depends on the purpose and sample size and shape of the sample. What do we look for one variable? Location and dispersion. Where are they on the scale? How much do they vary? Shape features, departures from symmetry, are there extreme value, are there gaps or modes in the data, and so on. Or agreement with a parametric form, does it look like a sample from a distribution that you think you can write down mathematically, or any other special features relevant to the context. So I'm going to I won't just rush through all these and say these things. Here's a little example from a classic statistics textbook. Dorsal length in millimeters for 94 octopods. I've been trying to find out where I've been using these data before, and other lecturers have as well. I think they were measured in 929 and somewhere in the British Museum, and I can't quite find the original data. But they're in millimeters. There's all sorts of species of octopods, little mollusks. This is the dorsal length in millimeters. They're quite small, 5 millimeters going to 190 millimeters. And here are the measurement of it. You already put them in numerical order, so you can stare at that and see the sort of numbers they are. So I'm going to illustrate a few things. First, the histogram. That's what people like to look at. And I just read it into R and just said histogram variable called dorsal DL, dorsal length, and just typed histogram, dorsal length. And it came out with this graph. This is the default histogram if you don't do anything other than just type histogram in R. And it looks like that. But one of my messages is that when you look at the default plot of something, it might be okay, but it's usually not what you want in the end. happy with the default version. But anyway, this looks rather beautiful, and you see there's a lot of small values and a small number of high values spread out like that. So what is a histogram? You group the observations into bins of equal width. Usually, classically, a histogram, the area in the box, in the rectangle, is proportional to the number of data values in that interval. So that's what it is. And so you could have non-equal intervals. I don't think I've ever seen a real example where I wanted to have non-equal intervals in a histogram. If you have equal intervals in a histogram, of course, it's the height of the box also is proportional to the number of data values in that interval, and that's what's tend to be plotted on the y-axis. It does it like that. And if you've got a reasonably large sample, then you can see a sort of shape features of a distribution. One of the things that's mostly important, which I haven't said anywhere on these slides, of course, I have some important things to off the slides, is that if you knew this distribution, what would it tell you? What is the distribution you want? These are just some data that happen to be collected. Is it a distribution that represents some real population? That distribution. I don't know. I've done another histogram here where I've shortened the bin width to 10 millimeters. Those ones came out with 20 millimeter bin widths. I've halved them to 10 millimeters, and this is the histogram here. I've done a couple of other little things. I've turned the Y labels around so I can read them, and I've put a few summary statistics on the graph. And always try to add details. Graphically helps you. 94 observations, median standard deviation written there on the graphs. But notice it's very different from the first one. And you might think it's not so nice because it's not a nice smooth curve going down like that. But it depends what you mean by nice. Now I know physicists like things to be smooth. Statisticians like things to be a bit rough, actually. I like data that's got rough, because then I know if it's all random, there's nothing more to explain. So I'm happy. If it's too smooth, I get worried because I don't know what's supposed to be. But yeah, anyway, there it is. And you could ask yourself whether that's better or worse. As far as looking at data is concerned, rather representing a distribution, I think it's better because I can see more of the data. I can see these are just single observations, but nevertheless, they're spread out like that, and then there's a bunch in here, and I can cope with that sort of. Then I don't know whether there's something happening there or not, and probably not, but there you go. So that's another histogram. I've got some more histograms here. I took some from fission track lengths and angles just to show you some different histograms. I won't tell you what fission tracks, all that fission tracks are, but these are confined fission tracks. They're in a crystal apatite, a mineral, and you can measure their lengths by clicking on down a microscope. And if you take ordinary fresh, unannealed, we call fission tracks, they have a very tight distribution. They're with a median of about 16 microns. These are S fission tracks in chemical action, and a standard deviation of about 1 micron. And when you plot them, you go to a fission track conference, they always plot them on a histogram with 1 micron intervals like that. Always. Now, your lecturer in statistics will probably tell you, or if you did a default in R, it wouldn't plot that. It'd plot you going from about 11 to 19, and it's all spread out. But the reason we do this in fission track conferences is everyone uses the same bin width. You can do it in fission track work because they're so well behaved, these lengths. Underneath, they look like that. And this graph is showing you a scatter plot of the length against the angle of the crystallographic z-axis. And you can see that the scatter is much the same as you go along the angle axis here. There's no relationship between length and angle. in that case. If fission tracks are heated, they anneal, they shorten in length, and they do all sorts of strange things. They get wider and fatter when you etch them, and so on. But they shorten in length, and this is the essence of thermal history modelling. The fission tracks, if they've been heated into ground, they get shorter, and they get shorter not uniformly with angle. The ones at a high angle of the c-axis get shorter more than the ones at a low axis, and you see it's compared with this graph, it's all gone down, and it's gone down to a little angle like that instead of being more or less flat there. And they're all more spread out. The histogram of lengths, it's got a lower mean, and it's more spread. And if you shorten them more, these have been annealed, very hot temperature, and all sorts of other things begin to happen. But the mean is lower still, and some of them, there's a sort of splitting up here of tracks which are sort of broken down there, and you get two little modes in the distribution of the histogram there. Anyway, the point about the graphics is you couldn't see this if you didn't put them all on the same scales. There they are. You look at histograms on each other, all, and these are on each other there, and the distribution of angles. We won't talk about those today, but the point I'm trying to make here is when you've got data like this, you need to have a structure, put them all together on one page on the same scales. A number of conferences I've been to, PhD students have presented their work on a poster with beautiful graphs. Then you look at the scales very carefully, and they're all different, and you don't really know how to compare the different experiments. Right, kernel density estimates. I did the same thing with this octopods data. I just went into R and said plot density, dorsal length, whatever the word was, and it came out with this figure. Anyone not know what a kernel density estimate is? Okay, I'll tell you what it is. You've got to listen, I'll only say this once. You imagine your dorsal lengths plotted as a dot plot along a line. So there's 94 of them, and you put at least a little dot plot, at least a little dot. Instead of putting a dot there and counting the number of dots in the bin for a histogram, you draw a little normal density function, Gaussian density function, centered on that point. So the mean of the Gaussian density is that observation, and the standard deviation in this case is 10.9 millimeters. It's called the bandwidth. And so you replace your observations by little Gaussian densities, and then you go along, adding up the height of the density pointwise along the x scale, and you end up with this continuous curve. Now you can imagine drawing a histogram by a similar method, where instead of just putting the observations into bins, you have your bin, your rectangular bin, and you start your bin at this end of the data and count how many observations are in that bin, and it's none. You slide the bin along, and at each point when you slide it along, you count how many observations are in the bin. And it goes, suddenly it gets to 1, then 2, and down, and it goes up and down. And that would be a sort of more or less, that is also the kernel density estimate. That curve you drew would go through the top points of all the histogram, but other points in between also. And the histogram is like a kernel density estimate with a rectangular window, whereas this is a kernel density with a Gaussian window, or normal window, which is more continuous. The rectangle has a sort of discontinuity at the end, and so it's not as pretty. But you get a similar type picture if you did that. So it's called a kernel density estimate because it's a non-parametric estimate of the probability density function of the population that the observations came from. There's a lot of statistics you can't do. You have to end a sentence in a preposition if you teach statistics. There's no other way of doing it. So you can think of it as an estimate. These data came from a population which has a continuous distribution, and here's an estimate of that distribution, the density function of the distribution. Now, the key point about a Gaussian a kernel density estimate is what bandwidth do you choose? And this is exactly the same question. In a histogram, what bin width do you choose? For a histogram, it's the same question as what bandwidth do you choose for a kernel density. It's simply an empirical smoothing. There's no probability interpretation of this Gaussian. It's called a kernel. It used to be called a window. Now it's called a kernel. These things change. It's just a smoothing method. So you're smoothing your data to get a much smoother thing than a histogram. It has some advantage. If you read a book on kernel density estimation, they will tell you this is much better than a histogram. And as an estimate of a density function, it is better in a sense. It's better in the sense that it's continuous, and you're trying to estimate something continuous. That's one thing. And also, it doesn't have a nasty problem that histograms have that people don't often realise, is that the shape of the histogram depends on where you put the first bin. Not just the bin bit, but where you start the first bin. In my octopods data, I started it at 0, because I like simple numbers. 0 to 5, 0 to 5, or 0 to 10, and so on, 10 to 20. But if I started it at 0.2, I would have got a different shape of the histogram. So kernel densities don't have that problem, because you go over the whole range, and there's no starting point. But there are. That's the kernel density estimate. You can ask yourself, would you rather have that or the histogram to go away and look at? It's up to you to decide. Here's another one with a smaller bandwidth. The trick, of course, is choosing the bandwidth. Now I've chosen the bandwidth of 4.5 millimeters. So if I take double, that's the standard deviation. If I double that, it's 9. It's close to the 10 bandwidth I did for the histogram. It's a similar amount of smoothing as I did for my second histogram of the octopod data. And just to show that, I've drawn in that second histogram with 10 millimeter bandwidths in blue at the back there. So there's the nice kernel density estimate for the octopod data. Now it's a bit more wobbly, and you might think that's worse because we don't like wobbles, but we might think it's better because we can see there are wobbles. I don't know. It depends on your purpose. One of the things people get confused in my mind about comparing histograms and kernel estimates is I think they're doing different things. A kernel estimate is specifically estimating the density function, whereas a histogram is really showing you the data in a summarized form. It's a slightly different thing, and you can sort of see it in a simpler way. Anyway, you can look at that. Now I've got another one here, where I've at last taken logs. It's very hard for me to go all that long. I only do without putting a logarithm or something, but I've sorted out. It's lasted about till now. So I'm looking here of the natural logs of the dorsal length y. Not really having any good reason, except that it's looking more like something like a normal distribution. So if the log of dorsal length had a normal distribution, that would mean that the dorsal length itself has what's called a log normal distribution, which is a model that you can write down, and then you can do mathematics and go away and play with that. And I've drawn the kernel density estimate. I've used a similar amount of smoothing here and here. Notice it's a very different shape, of course. The scale's all different here. And it's got this, it won't go away, will it, this bimodal feature. There's two modes there. Now, I mean, it might just be random variation. We don't know. Now, just to show you, I've just drawn a little red curve as a normal density function superimposed there, just to show what that would look like. And you can look at that. So, I don't know what this distribution means, or whether this would mean it would have two modes, I don't know. But I can tell you that years ago I used to, before we had distractions with computers, I used to get students to measure the length of shrimps. I'd go down to Billingsgate early in the morning, bring them back for the statistics practical, and they would each choose 10 shrimps and measure the lengths and put them all together. This is quite an instructive exercise. It's not, if you haven't ever tried to do it, it's not so easy to measure the length of a shrimp. There's a lot of discussion about what you do actually measure. Do you stretch it right out and pin it down and do it? And what do you measure it with? And then by the time you've measured it, you don't really want to eat it, which is a bit sad. But and I did this for several years, and we got a class histogram of about 200 shrimps and lengths of shrimps. And every year, I tell you now, every year it had a bimodal distribution. It wasn't a nice normal curve that we thought we were going to tell the students that things are all normal. It had a bimodal distribution. It did. And I'm wondering whether these octopods do as well. No one knows why. I'm guessing there's two generations of young and old somewhere in there, or male and female too, but shrimps all look the same. But there you go. So if you ever want to see a bimodal distribution, go and buy some shrimps and measure their length. What about box plots? I'm showing you these because they're a sort of way of smoothing, a way of summarising a distribution, one variable still. Here the octopod's dorsal length, and what you basically plot is a 5-point summary. The smallest value, the lower quartile, the median, the upper quartile, and usually the largest value. But most computer programs will do it something like this. This is again done in R, and it plots extreme values separately as dots. And so this point here is the largest of all the ones, largest of the rest, that aren't extreme values. And you can define extreme values in any way you like, and the default definition is anything more than 1.5 interquartile ranges from the upper quartile. So the upper quartile, median is because of the midpoint, so half the observations are less than that and half are greater. Lower upper quartile, quarter or less than that, a quarter or greater than that, so the middle half of the data are in the box. That's the thing about a box plot. The box shows you the middle half of the data, and the median shows you the middle of that, and then these just show you extreme values and so on. So it's a sort of nice, simple way of getting, if you've got a large data set, a lot of data, you can summarise a number into that, and then you can do separate box plots for different samples or different cells. I'll show you an example of that. At the end here, I've written 94, which is the sample size. That's my own invention. If you do that in R, it won't like that. And if you want to go into computing and computer graphics and software, devise some better graphics that write the sample size on the box plot, because it's very important. If you don't have a sample size on the box plot, they can be very misleading sometimes. There's a sort of a few snags, but they don't work well with discrete data. Discrete data counts, they work very poorly. Don't do box plot with discrete data. They don't work well with anything which has got some shape other than unimodal, bimodal. You lose that sort of information in a box plot. For those, dot plots are better, but you can't. There's no good computer software that draws dot plots. You can draw your own, if I can see. But anyway, they're box plots. Here's some more box plots for the air quality data that I started with before. And I'm showing you this, it's pretty simple. What I've done here, for each month, I've drawn a box plot for the observations in that month. So I'm plotting you monthly distributions rather than the daily time series. So some information is gone. It's the time series within months is gone. I'm sort of just putting them all together in a distribution. But you have to use summary statistics when you've got lots of data sometimes. But I think it's quite a good trick with long time series of many variables to plot a time series of box plots to smooth, so you can see how the monthly means go up and the medians go up and down, and how the scatter increases for the high values and goes less for the low values. And I haven't put the sample size underneath, which I should really have done, but they're all roughly 30 because they're months. So that's a trick with, and you can stare at these with box plots. QQ plots, I just put these in because if you wanted to know say for the octopus data, does it look like a log normal distribution or log normal distribution? The way a statistician would do this would be something like a QQ plot. What do you plot? You plot the ith smallest observation on the y-axis against the theoretical quantile for a standard normal distribution on the x-axis. So you imagine a standard normal distribution. So you've got 94 observations, and you divide it into 94 equal areas, and you take the midpoint of each little area, and the smallest one of those gets plotted against the smallest observation, the next smallest gets plotted against the next smallest observation, and so on. Now, we won't go into the theory or the mathematics, but someone's already done that, so we don't have to. But if you do a graph like that, if your data did come from a normal distribution of any sort, then those points would lie along a straight line, roughly. And the intercept with 0 of that line would be the mean, mu, and the slope of the line would be the standard deviation, sigma, of the normal distribution. So here I've done it for the dorsal length of box plots. And you see it's not along a straight, it's curved. And when you get good at looking at those things, you can see that it's positively skewed because it's curved that way rather than the other way. And there it looks like that. And I've drawn the straight line in there, which has mean equal to the sample mean, which is intercept equal to the sample mean of the data, and slope equal to the sample standard deviation of the data. Now, if you do that in R, it will tend to plot differently. Not a very sensible one in my way. That's a better line to plot than the one that would do in R. But that's also easy to do. Now I look at the log of dorsal lengths, and lo and behold, they go beautifully along a straight line. And you mightn't believe me, but that is beautifully long. It's almost too good. And to see that it's too good, what you can easily do is to take random samples of 94 observations from a normal distribution and do a QQ plot of those and see what they look like. And they'd also go along a straight line, but not as beautifully as that, usually. We do lots of them. Just flash them through on the screen, and you get a feel for what they should look like. So it's almost too good to be true. So if you're a statistic lecturer, you love that because you teach the students that everything's lovely and normal. But yeah, it's hiding something there. But anyway, it's a good way of looking at. You can get, if you want something to be normal or any other shape, you can do a QQ plot against that distribution and look at it like that. Now I'm not going to get through anything like all the examples. I didn't think I would. So I don't know whether you want me to. I'll say something about several variables, very quickly, I think. The thing about graphics, plotting one variable is okay, well and good. And I'll repeat what I said before about those plots I've just shown you. They're even better when you put them together in several samples or in time series, and you can combine histograms or box plots or density functions and so on, and see how they change in sequence. Several variables. This is the great challenge of graphics, is to see as many more variables together on a graph. And you can get up to about 5 or 6, and then it gets very hard to compare more than 5 or 6 variables together. But anyway, standard methods: pairwise scatter plots is the command pairs in R. Conditional plots is a command called coplot in R. Use different plotting symbols or colours to distinguish different variables and so on. And you're looking here for location, spread and shape as well, but relationships between variable, any pattern, partial linearity for relationships, any patterns which might have some interpretation in your case, and of course outlines, stream values. So here is a pairwise scatter plot of the ozone, the air quality data, and here I've now forgotten completely that they're time series, which in one way is naughty, but in another way it's not that naughty because we're not looking at the time dependency. We're looking at, and actually you've looked at that original plot, there isn't that much time dependency anyway. and how they relate to each other, these variables. And so the idea of a pairwise scatter plot, you can see labeled here. So ozone, this one, what that means here